Okay, on to chapter 15. So for this one, we're actually starting to talk about benzene compounds, and we'll talk more about the reactions in the next chapter. But this one is mostly just sort of an introduction to benzene. So the first thing we have to do is to look at to name the compounds. Okay, and so these are 6 of the. So first thing we're gonna have to do is we have to know some of these sort of base names. How about that? So if there's one methyl group, we call it toluene. Only one. So like that. So if there's an OH, this is a phenol. This is directly attached. If there's an H2, it's an aniline. If it's a CH2 methyl like this, so it's CH2O, sort of a ketone group with a methyl one here, it's an acetophenone. Here they actually abbreviated this, so benzaldehyde, right? So it's an aldehyde. So it's abbreviated CHO, but that means this here. That's the abbreviation for an aldehyde group. And this one over here, it's benzoic acid. This one here, so whenever you see CO2H, that's what they're talking about, is a carboxylic acid group here. The reason why it's CHO is to distinguish it from COH. You might think that would be the C with an alcohol on it, and so they write it CHO for that, and they just got lazy and wanted to be able to squish this all together. So like that. So, but benzaldehyde has the aldehyde hanging off of it. The benzoic acid has the carboxylic acid going off of it. I'm not going to make you know the xylenes. So that's two methyl groups, or the styrene, which has a double bond hanging off it. This gets complicated in a hurry, but if you know these 6, it's fine. So with that, so for naming compounds, right, the first thing you got to do is you have to say, and remember, toluene only has one methyl group on that. If it has more than one, you wouldn't worry about that. You don't consider that a toluene. Okay, so the first thing you got to ask when you have a benzene is, do you have one of these base structures? If you do, right, so it's a real quick statement. So yes, I do. Okay, so then you have to say, okay, so if there's more than one base structure, then you have to use the priority rules, stuff like that. So, and basically what I'm going to throw at you is, if there's 2, basically everything is going to be higher than a toluene. So like that. So toluene sort of in the middle. Everything else, base structures are higher than that. If it's not, then we just consider that if it doesn't have a base structure, then it's just a regular benzene. But if there is, then you'll have to use one of those. So like that. And then from there, right, you're going to name the side chains, right, determine the attachment points. But the nice thing with base structures is that wherever that is, right, so if there's about benzaldehyde here, right, this is automatically going to be carbon 1, right? If you have benzoic acid, no matter whatever else is sitting on there, right, this is always going to be carbon 1, right, for the benzoic acid. If you have a base structure where that's going to reference where carbon is on that ring, something like that. And then so you put for getting the, and then you just go clockwise or counterclockwise and figure out the lowest number, right? So with that, and so for this one here, the alkyl, put them in alphabetical order, stuff like that, and put the base name at the end, just like we normally do. Now, if there's not a base structure, so with that, and notice like halides are on there. There wasn't a bromobenzene or whatever. There wasn't a structure for that, right? If there's no base structure, then you just then your main chain is going to be benzene. You find the side chains, determine the attachment points, just like you would do with a cyclohexane, right? So you have to figure out. You start each one at 1 and go clockwise, counterclockwise to figure out where which is going to be number 1, and then attach it normal, and then put benzene at the end, stuff like that. So okay, so here we go. So this one here, right? So sorry, bromine there. So okay, so here we go. So we don't have a base structure in here, right? So our base name is going to be benzene. We know that, right? We have a bromine, right, and we have a chlorine. All right, so bromo, and then chloro. All right, so bromine is going to be bromo, chlorine is going to be chloro. All right, so now we need to figure out the numbering, right? So we're going to say, well, what if that's the chlorine's number 1, right? So with that, so if that's the case, this is number 1, right? The numbering, we're going to go towards our nearest side chain neighbor. So 1, 2, 3, 4, 5, 6, right? So that would be 1, 3. Right, so if we did it here, we said, okay, that's number 1, right? So then it'd be go counterclockwise here, 2, 3, 4, 5, 6, right? Because we're doing towards the nearest neighbor here, so that means 1, 3, right? So these both add up to 4, right? So like that. But in the case of a tie, an absolute tie, right? We pick the one that's going to give the first alphabet. The 1 goes with the first alphabetically, so it ends up being 1 bromo, 3 chloro, benzene. There you go. Okay, so here we go. So here's this one. Okay, and so nitro, these sort of nitro groups don't have a base structure right here, but we do have a nice toluene here. Okay, and I'm going to circle that, the toluene, because this methyl group is going to be associated with the toluene. Okay, so we've already named that methyl group, right? Toluene. Okay, so that methyl group is in there. So that's associated with the toluene. So we don't have to name that. We've already named it. Okay, but we do, however, have these 3 nitro groups. So nitro, nitro, nitro. Okay, but now we know that this is going to be, right? So we know that this is 1. Right, so 1, 2, 3, 4, 5, 6. Right, so we go clockwise. So it'll be 2, 4, 6, 2, 4, 6. Right, but you have to take a look at the other way too. So 1, 2, 3, 4, 5, 6. Right, so again it'd be 2, 4, 6. Okay, so you add them up. Right, so they're both 12, and it turns out that it would end up being the same number. No matter which one you picked, it would be the same because they end up being 2, 4, 6. Because there's 3 of them, trinitro toluene. Okay. So here we go. So T, N, T. So this, right? So T for the, right? So it ends up being T and T. So trinitro toluene. Okay, so this is the structure of TNT. How about that? So the last one here, right? So we said, okay, and so, right? So we have two base structures here, right? So this is phenol. Okay, so that's phenol. Okay, and that's toluene. Right? And for the priority rules, everything's a higher priority than toluene, so we're going to say this is our base structure. So this is phenol. Okay, and so now we need to do the naming, right? So it could be, so we have our methyl group here, right? So now this methyl group is not part of phenol, right? The OHs, but the methyl group isn't. So we need to figure out where that is, right? So it's either, right? You can do clockwise, 1, 2, 3, 4, 5, 6. So it'd be 4. If we did the red numbering, it'd be 1, 2, 3, 4, 5, 6, right? So it'd be 4 again. So 4. So it doesn't really matter. And so which way you choose, because it's gonna be the same numbering scheme. So it'd be 4-methyl phenol. Okay, so there you go. Okay, now remember with the cyclohexanes, sometimes there are times where you have your ring hanging off of something really big and stuff like that, and so then the cyclohexane or whatever it was became the side chain. So, but that same thing happens here. So if you have directly on here, right? So if you have benzene hanging directly off the main chain, notice it has 1, 2, 3, 4, 5, 6, 7, 8, right? This is bigger than this. So this side chain, this benzene becomes a side chain, and so we call this phenyl. We'll talk about this in a second, why it's not benzyl, which would make sense. Okay? If it's coming off of here, so if your side chain is coming off of here, but it connects through a CH2 group, okay? So to your molecule. This is actually called a benzyl. Now, it would make more sense that it would be this, right? The problem is, this was accidentally discovered first, and they thought it was just benzene. Turns out that it's not. It has this CH2 group. It's more like a toluene. It looks like a toluene, right? If you plucked off one of those, right? So if that was a CH3, that would be toluene. So like that. So it turns out that what they discovered, as it turns out, ended up being a toluene moiety on it, but they never got around to renaming it, so like that. And so then this benzyl stuck, so they had to figure out another thing to do with just a regular benzene hanging off of the main chain, and so they called that phenyl, stuff like that. So it's one of those quirks that we just sort of, it's been around for 100 years, because they discovered this on the gas lights that were in London, the soot that came off of that, stuff like that. So 150 years ago, they discovered this molecule, they figured it out, and went on from there. And so the problem is they've been naming it for last 150 years, and nobody's cares enough to go in to go in and fix it, stuff like that. And so now undergraduates have to suffer, stuff like that. So this is a phenyl, this is a benzyl, stuff like that. So okay, now there is another ordering scheme, stuff like that you guys need to know. Okay, stuff like that. And so this is going to become much more important next chapter. Okay, and so if your group is here, right? So this position here and here, this is the old naming scheme. This is called the ortho position. So it doesn't really matter which side. One carbon away from whatever it is that you're interested in. One away is the ortho. Two away is the meta. And down below here, 4 away, 1,4 is para. Stuff like that. So it doesn't matter which side it's for meta. It doesn't matter which side it's ortho. It's a 1,2, 1,3, and 1,4 positioning on here. This is going to become more important next semester, but next chapter. But do know that this, and you can come in and say, if you have two things attached, you can say, oh well, they're ortho. Instead of doing the numbering before, you could say that they're ortho, but it only works with 2. And sometimes it becomes an issue with which one gets the priority, and anyway, stuff like that. So it becomes, well, I guess it's not a big deal, but it could be kind of a pain in the neck, stuff like that. If you number it using the ortho meta para and it's correct, I'll give you credit for it. It's not a problem, stuff like that. But when you're first learning it, do try to use the numbers, because it's much more systematic in what you're doing this. But we're going to need to know this for later, stuff like that. So. But for benzenes, okay, so this was a huge debate about the nature of benzene, and it lasted most of the 19th century, so all the 1800s and stuff like that. Because it turns out, so if you take cyclohexane, you come in here, you add a double bond, one double bond, it's like this, 2 double bonds, and then 3 double bonds. It becomes once you hit 3 double bonds in conjugation within these within the cyclohexane, you get this huge drop, huge stability fallout and stuff like that. And so there's a huge amount of debate on why and stuff like that. And so it turns out what's going on is that you have these pi bonds in a row, stuff like that, and they're going all the way around the ring and stuff like that. And so the electrons can literally just spin around the pi orbitals there, just keep going, right? So if we move 2 of those, right, they have to sort of bounce back and forth like this, but you put them all in a row, stuff like that. So all 6 of them have it. You can go spinning around and stuff like that. And so and so that gives a massive amounts of stability to the molecule and stuff like that, more than you would expect. Now, just as a reminder in the drawing, right? So these are 2 resonance structures for benzene, right? So showing the alternating double and single bonds. And what's more accurate to actually show is actually just putting a circle in the middle of it, just to indicate that it's actually everything is a 1.5 bond, and that the electrons are actually smeared all the way around it. But sometimes this is nice because you need to show that you're reacting with the double bond, but this is probably the more accurate of the 2 interpretations of what's going on and stuff like that. And so how do we tell if something, and so it turns out that how do we know if something, particularly with a ring, how do we know if something is acting like a benzene and how if something's acting with just individual double bonds and stuff like that? And so what's happening is when something is acting like a benzene, we call that to be aromatic and stuff like that. And so and it's aromaticity, that's the word, and stuff like that. If it's not acting like so if it acts like a benzene, we call it aromatic. If it's not, then it's called anti-aromatic. And it turns out that there's a couple of different rules for this. One, you have to have everything be able to, like all the carbon atoms, in this case, be eligible to be with a resonance structure, right? So it either needs to have a charge, a lone pair, or be part of a double bond, right? So when it has those, the reason why those would be eligible is because those have a p orbital available to them. stuff like that. So the compound must be planar, it must be flat, right? Because we make sure all the p orbitals are they're not like sticking out in weird angles. They can be all aligned, right? So like that, and it has to satisfy this. Either has to have 2, 6, 10, 14, 18, and goes up 4 from there. Now the way that you get this is through this calculation, but the most important thing is it either has to have 2, right? So 2, 6, 10, 14, 18, 20, sort of, and so on. So these are the Huckel numbers. Okay, so it has this amount of electrons in the ring, then it's considered aromatic. Okay, and so if we look at this, compound here, right? So it's in a ring, right? Everything's part of a double bond, but how many pi electrons does it have? This one has 4 electrons, right? So 4 pi electrons, right? 2 here, 2 here, right? So that's here. So this is part of this. Doesn't have a Huckel number, so this is anti-aromatic. If it doesn't satisfy, it has to satisfy all of the requirements. If it does, then it's aromatic. Otherwise, it's not. Okay, and so this one here, right? So this one better, right? So for benzene, right? So they all have p orbitals, right? So they're all connected to a double bond, right? But it has 2, 4, 6 electrons, right? 6 electrons, pi in the p orbitals, right? So here we go. So this is aromatic, right? This one here. So we have an 8-membered ring, right? So here, and here. I'm sorry, I just rotated it, but it doesn't really matter. All right, so 2, 4, 6, 8 electrons in it, right? So that's here. So this is anti-aromatic. The reason why we call these aromatic, by the way, is things are aromatic, right? They smell, right? So like that, and so that's why they were originally interested in these compounds, is because they smelled good. Well, either smelled good or smelled bad, and they took a look at these, stuff like that. So that's one of the reasons why they call them that. But as long as it has this Huckel number of electrons in here, you're good. It's your aromatic. So there you go. Okay, so you can also have this with anions, right? Stuff like that. And so what you can do is you can say, okay, if you've got something like this, right? Right, so these part of double bonds, right? This one has a set of lone pairs, so all of these are eligible. Well, how many do we have? Well, this is 2, this is 2, this is 2, right? So this 2, 4, 6 electrons, right? So it's aromatic. It satisfies the requirements. Okay. Same goes with this one here. 1, 2, 3, 4, 5, 6, 7. Right? Right, so there's a positive charge here. Right, so here we go. So we have this one here. We have 2 electrons from there, 2 electrons from there, 2 electrons from there, 2, 4, 6. Right, and they're all eligible to be part of that resonance structure, right? Because this one, these are all double bonds, right? This one has a charge, so it's eligible, but it has 2, 4, 6 electrons, 6 pi electrons, right? So again, it's aromatic. It satisfies the requirements. So this acts like an aromatic. This acts like an aromatic. This one does. These don't. These act like individual double bonds. They're conjugated double bonds, but they act more like double bonds. Stuff like that. So because what it can do is it can put these 2 electrons up into that pi orbital, or into that p orbital, right? And so you get that there. Here, what it can do is it can at least has a p orbital that it can extend out and put into the plane with these guys here, so that the electrons can at least swing right through it. It doesn't have one to contribute, but it does at least have a pi orbital to contribute, so the electrons kind of whirling around here, stuff like that. So now for heterocycles, right? So rings that have more than just carbon in them, right? They're going to have lone pairs associated with them. So usually it's nitrogens, oxygens, sulfurs. There's some other ones, but those are the main ones that you see. And so it turns out that what it does is it with the lone pairs, it either adds them or puts them 90 degrees away from the ring, so that it can get to these Huckel numbers. Okay, and so what it does is it says, okay, so if you have a nitrogen here, right, so we have pyridine here, right? So what it does is it says, okay, if I just have these 3 sets here, so 2, 2, 2, right? We're good. We're at the 6, right? But what it does is, oh crap, I've got these lone pairs. What do I do with them? And so what it does is it sticks these sticks out 90 degrees. Right, so it sticks these out 90 degrees away from the other pi orbitals, right? So it can stay with just 6. Okay, if it added these two in there, it would be sunk, right? So you wouldn't have, because you get so much stability out from being able to be aromatic, that it basically does what it needs to do to become aromatic and stuff like that. So the other thing it can do is it can move them into the ring, right? So like that, and so what it can do okay, and so you've got these two, right, which would normally make it, right, so we've got these two, but we also have, 2, 4, right, so it's anti-aromatic, but what it can do is it can actually move this guy into the plane to give that 2, and then these are out of the plane. These lone pair, right, so there's a lone pair here, and there's a lone pair here. It can move these out of the plane, and these can sort of move into the plane, into plane of the pi bonds, into those p orbitals, right? So now it's 2, 4, 6. So now you've got 6, and so now you're antimatter. And the long and short of it basically ends up being when you have a heterocycle like this, it's going to do with those lone pairs what it needs to do in order to become aromatic. Okay, it's either going to stick them out to the side so that you don't have to add the 2 to make it anti-aromatic, or it can move them into the plane, right? So 2, 4, right, to get them into the plane to provide the 6, stuff like that. And so it's going to do, so 99 times out of 100 or more, the molecule is going to move those lone pairs how it needs to in order to become aromatic, stuff like that. So okay, so now these things are incredibly important in biology, right? So a lot of the DNA and RNA bases, cytosine, thymine, uracil, they are these heterocycles here. They're aromatic heterocycles. The histidine of the so this is the imidazole of the histidine amino acid side chain here, stuff like that. So that's what that does. Okay, you can also get stuff like that. It's incredibly important. You can also get these fused rings here that are so when you have this, it becomes more complicated to figure out aromatic, non-aromatic, right? So these are going to be aromatic. Okay, these fused naphthalene, anthracene, benzopyrene, stuff like that. They're going to act similarly to benzene. They're going to be aromatic. And it turns out, again, we'll talk about this in the next chapter, that the way the benzene reacts is going to be different than than just a set of lone pairs, right? So if you add bromine in here, you add a little bit of iron to this, right? So if you just had a lone pair, right, you would add bromines to both sides. But what we end up seeing is that we just get one bromine on here, and stuff like that. And so when you do these reactions, you sort of realize, something different's going on with this. These guys here, what they do is they are completely flat. All of their p electrons are in a line, stuff like that, and so they're all sort of smeared around and stuff like that. So same goes with the heterocycles, right? They're going to do what they need to do in order to become aromatic, and these become incredibly important. The adenine and guanine DNA bases, right? So these are polycyclic aromatics. The tryptophan is one. Quinine, right? So this is the first real good antimalarial compound, stuff like that. It has a nice polycyclic aromatic, stuff like that. So now the spectroscopy of these things, right? So you can actually do a little bit of IR and tell what it is. If it's mono, it's meta, ortho, meta, para, stuff like that. And so these are the ones. So this is so like I could give you this chart and say, okay, you've got a bottle. It's going to be one of these guys here, and if it's at, let's say, the only reading you get is 750, well, it would be like these both have absorb at 750 and these two don't. But remember, it's with IR, it's what's there and what's not there. In order for it to have been the mono substitute, it would have also had one at 700, so it would have had to be like 700 and 750. Where this one, we're just getting the 750, it's that means that it's the ortho substituted. If I were to say, okay, it's 700 and 820, right? So like that. So 820 would be both of these, but since we also have that 700, it's the meta substitute. So it's this one, I'm sorry, the ortho substitute, which is here, and this one would be the meta substitute there. So you have to remember this, and that you have to remember with IR it's there versus not there, right? So like that, and I would give you this chart and say, okay, here's the situation, this is the bottles, what do you have? So that'd be a nice multiple choice question. Stuff like that. So for UV spectroscopy, things with double bonds, aromatic groups generally absorb in the UV range, stuff like that. So now with IR, as you said, but you can't really say much about it. Now for NMR, it's actually quite interesting, right? Because if you remember back from the NMR, stuff like that, so the things in the aromatic groups were shifted way downfield, right? So they were unshielded from those electrons, right? And the reason is right, so you're going to have these electrons whirling around. Whenever you have a charge moving around, you also create a magnetic field, right? So you actually get, so you have this induced magnetic field within these whirling around electrons here, and so that de-shields these hydrogen atoms, stuff like that. So stuff like that are sitting out here, and stuff like that. And so that since they're feeling the electron, the magnetic field a lot, you're going to get shifted downfield. Now, to test this, what you could do is you could say, okay, let's make a really big one where we have hydrogens in the middle and hydrogen on the outside, and that's what we see. These guys are, the blue ones are de-shielded, right? So they're at 9.3. The ones in the middle are really moved out. This is really moved way upfield at -3, right? Which is what we would predict, right? If this is going to be de-shielded, these are going to be exceedingly de-shielded, these are going to be exceedingly shielded, and stuff like that. And so that's what we see. So like that. So this this compound was just confirming what we know. So like that, we can also get these effects with things that are just outside of the aromatic, right? So the benzyl or benzylic, which is a carbon attached to a benzene ring. These things are this CH2. These hydrogens would normally be at 1, but this one's closer to 2.5 to 3, stuff like that. And so you're sort of seeing those effects of the de-shielding. This also affects the carbon NMR as well, right? So these guys here, they are also shifted way upfield because of this induced magnetic field from the electrons whirling around from this magnetic field. Okay. Lastly, stuff like that is to talk a little bit about the aromatic compound, these what are called NSAIDs, stuff like that. So these non-steroidal anti-inflammatory drugs, typically they're used for pain relief, and fever reduction, stuff like that. So it turns out they're using cyclooxygenase inhibitor 1 and 2, stuff like that. And so this is part of the immune response, or so the inflammatory response within the body. So the first one was actually done in first really good one that was discovered was salicylic acid, which is isolated from willow bark. So people would either chew on willow bark or they make willow bark tea when they had some pain, and it would be pain relief, or if you had a fever, you would get that. With that. And so it turns out the problem is the stomach lining. So when Bayer came in and started mass producing this, they started mass producing salicylic acid. It was great. The problem is the stomach lining it has to be resistant to the acid, stuff like that. And so what it does is it's constantly getting degraded and stuff like that. So your body just makes a new stomach lining every couple of days and stuff like that. Well, it turns out that salicylic acid blocks one of the enzymes that's responsible for rebuilding your stomach lining, and so now no new lining. And so after a while, of taking salicylic acid, you would start getting really nasty ulcers because you'd be blowing holes in your stomach wall, stuff like that. So it turns out that if you put an acetate group here, you mix it with acetic anhydride, it prevents this inhibition, right? So it can't do your stomach lining is just fine with this, and so you can go on and you can still use it. It works pretty well. I mean, we've been using it for the last over 100 years, and there's not a whole lot of drugs that aren't snake oil that are from that time that we still use, but that's one of them. So with that, and if you look at ibuprofen, which is using Advil, and Aleve and Naproxen, they look very, very similar to it, right? So you've got a benzene ring here, you have this carboxylic acid group on this at this end, like that. So Tylenol, which is acetaminophen, is a little different, stuff like that. So it works on a different mechanism. It turns out in the late 80s, early 90s, we were designing these drugs, and we said, okay, we know what COX-2 is, stuff like that, and so let's pick one. COX-2 is the ones to resolve for pain, and so what we're going to do is we're going to say, okay, we're going to make one that's very specific for COX-2, stuff like that. And so they did, and they're two of the more more important ones are celecoxib, which is Celebrex, and Vioxx. It turns out the problem with just inhibiting COX-2 is that you have issues with your heart. I think it's a heart valve issue, but I could be wrong. But it's basically what happens if you're on a long-term maintenance for pain with just COX-2 inhibitors, you would be increasingly likely for a heart attack and stuff like that. And so there was a huge issue with Merck and COX-2. With Vioxx, it wasn't that it was causing heart attacks. That was bad enough. The issue was the fact that they denied it, stuff like that. So, you always say it's not the crime, it's the cover-up that gets you in trouble, and that's what got Merck in trouble with this. Celebrex is actually still on the market, but with warnings of saying how, it's just for short durations. It's a great pain drug. The problem is it just has this issue with increasing your likelihood that you're going to heart attack, stuff like that. So, but that's just one of these things. So, thanks.